Welcome back to another deep dive. We're continuing our series for all you number theory students out there, exploring the incredible online encyclopedia of integer sequences.
That's right, the OEIS, always fascinating.
Today, we're zooming in on one specific entry. Sequence A000297. We're basically going to unpack the official OEIS page itself.
See what it tells us.
So at its core, this sequence, A000297, it's got this neat algebraic formula. AN equals n plus 1 times n plus 3 times n plus 8, all divided by 6.
Pretty straightforward looking, algebraically speaking.
Yeah, and if you calculate the first few terms, you get 0, then 4, 12, 25, 44. It keeps going like that.
Okay.
But here's where it gets really interesting, I think. That formula looks, well, purely algebraic, doesn't it?
It does. Just a polynomial in n.
Right. But the real kicker, the surprising part, is what these numbers actually count. They have combinatorial meaning.
Exactly. And that's often the magic with these sequences, isn't it? You have this simple-looking rule generating integers, but then, boom, it turns out to be counting something, well, something tangible in combinatorics.
Precisely. It's like finding a hidden code. So the OEIS entry gives us some great examples. One of the main ones is for n greater than 3, an, is the number of triangles in a specific graph.
Ah, yes, the Turán graph.
The Turán graph T, N, and 2, yeah. For those maybe not familiar, Turán graphs are really fundamental in extremal graph theory. They're kind of built to avoid certain structures.
And the fact that this specific polynomial formula nails the exact count of triangles in that specific graph.
Oh.
Well, that's elegant. It shows this deep link between algebraic form and, geometric or structural properties.
It really does. It highlights what the OEIS does so well, acting almost like a translator between different mathematical areas.
It's a bridge, definitely. And there are other interpretations listed too, right? I think there was one about counting subsets in a particular way.
Yeah, exactly. For n is 4, an5 counts how many n3 subsets of an n set intersect two specific two-element subsets. It's maybe a bit more abstract to visualize immediately.
A little bit, yeah.
Right.
But it reinforces the same point. This one sequence pops up in different counting contexts. It's surprisingly versatile.
So beyond these really cool combinatorial interpretations, what else does the OEIS entry tell us about A000297?
Well, it offers more tools, more ways to think about the sequence. Like the generating function is provided.
Ah, right, the generating function.
Which is 2x squared divided by 1x to the 4th power. And generating functions, they're incredibly powerful. It's like packing the entire infinite sequence into one single compact expression.
It encodes the whole sequence, basically.
Exactly. And from that function, you can often derive things like recurrence relations or asymptotic behavior, stuff the simple polynomial formula might not reveal as easily. It gives you a different sort of analytical handle on the sequence's structure.
That makes sense. And it's not just theoretical tools, is it? The entry seems pretty practical, too.
Absolutely. That's another strength of the OEIS.
Yeah.
It usually includes code snippets. For A000297, you've got ready-to-go code in Maple, Mathematica, Python.
So you can actually compute terms easily or use it in your own project.
Right. It connects the theory directly to computation. It makes the sequence accessible for experimentation and practical use.
Okay, so let's pull this together. What's the big takeaway from this quick dive into A000297? We started with this fairly simple formula, n plus 1, n plus 3, n plus 8, 6. And we found it connects deeply to combinatorics, like counting triangles and Turán graphs. And the OEIS entry itself gives us even more the generating function code implementations.
It really raises an important point, doesn't it? How a single sequence entry, when it's well documented like in the OEIS, can be this powerful hub.
A hub, yeah, I like that.
It connects abstract algebra to specific counting problems, and then even gives you the tools to compute it, all in one place.
It really makes you think, how can a simple algebraic rule describe something like the number of triangles in a graph so perfectly?
It prompts you to wonder about the deeper patterns, right? These hidden connections running between different fields of mathematics that integer sequences often reveal. What else is out there? Maybe already cataloged, just waiting for us to notice the link.